spectroscopy topic. It's far and away the coolest. Has anybody ever gotten an MRI? You don't have to raise your hand if you're uncomfortable answering that. But all right, so MRIs are actually similar to NMR. However, they didn't want to use the word nuclear on the equipment because that freaks people out. However, the physical phenomenon that we're going to learn about applies the same way to MRIs as it does with small chemical samples. The main thing with NMR is to remember that atoms and nuclei have atomic spin. Specifically when they have an odd number of protons. Or neutrons. And let me describe what I mean by this. And specifically, we're going to focus on the nucleus. So I'm just going to draw our generic nucleus as a circle. It's got a positive charge because it's a mixture of protons and neutrons. And if we look at this, it's going to actually spin around kind of like a top, right? What happens when charges spin? Anybody taking physics?
Centrifugal acceleration.
Magnetic fields. So if you take a charged object and you spin it around, you can actually create a magnetic field around it. So nuclei actually have this, where they've got this magnetic field that is exuded going up and down. So just like with magnets, you'd have your north pole and you'd have your south pole. And if you've taken physics, you can actually follow that thumb rule, right? I think I'm doing it the right way. I haven't taken physics in a while. So if you imagine a bunch of atoms floating around in solution, they're almost like spinning tops, right? So the picture on the left shows these pictures of spinning tops, and they're kind of just pointed in any and all directions. However, the principle of an NMR spectrometer is you want to align these in a magnetic field. So how can we align a bunch of spinning little magnets in a magnetic field? Yeah, use a bigger magnet, right? Atoms are tiny. We can get super strong magnets from semiconductors. And so what I have for you guys to show you a little bit of this principle in action is a demonstration. Hopefully this will open. It'll open on this one, I know. I am recording. I'm pretty sure. Yep, we're at 27 minutes. All right, so let's take a look at this. Come on. Won't go full screen, but don't freeze. All right, so if you look at this, a nucleus is pretty similar to a compass where you've got this little magnetic field. And what we do in an NMR is we actually take a really strong magnetic field which will cause it to align, right? So the north pole of your spinning nuclei will be aligned with the south pole of the bigger magnet and vice versa. And then the question is, well, why is this useful? And there's a phenomenon called resonant frequency, right? So let's say I've got another magnetic field and I bring it in from the side, right? I can knock it off axis a little. So imagine that I start pushing this magnetic field at a frequency, right? It's not really doing much. However, if I slow down, it's kind of like pushing a kid on a swing. You've got to push it at the right frequency, and when you do that, you hit something called a resonant frequency, where you can knock a nucleus completely off axis from a magnetic field. That's exactly the principle of NMR, is you take your sample, you align it in this giant superconducting magnet or permanent magnet, and then you use a perpendicular electromagnetic field to knock your nuclei off axis, and then it will align back into the magnetic field. So let's take a look at another diagram. because I know this is fairly abstract. So imagine knocking it off axis, and then it's like a top. So a top, when it goes back into the magnetic field, kind of whips around back into that larger magnetic field that's being applied by the instrument. And so this is exactly what an NMR does, is it will knock your nucleus off axis and then wait for it to relax back into the field. And when it relaxes back into the field, you've got these detector coils around your sample that will actually pick up that energy. So let's go back. Yep.
What's the benefit of knocking it over and waiting for it to go back?
Well, we'll get into that. It tells you a lot of information about that nucleus and neighboring atoms to that nucleus.
Why it increases on the z-axis?
What's that?
I mean, why it increasing on the z-axis?
So imagine we've got our top, it's aligned on a magnetic field. We knock it off axis, but it's going to be attracted back into that magnetic field, right? It's going to whip around until it relaxes back into that field. That's essentially all an NMR or an MRI does. I know right now it seems super abstract, but I wanted to explain the physics behind it before we get too much further. So let's go back. I'm going to delete this. And let's kind of describe what's going on. So we align nuclei in a magnetic field. A second perpendicular field. Actually, let me say electromagnetic field. Knocks the nuclei off axis. A detector records the relaxation of the nuclei. So let's think about it. If we try to record the relaxation on a 2D graph, because we don't really have 3D graphs, essentially what will happen is it will be off axis and then it will start relaxing back into plane. So do you guys remember that 3D thing? As it whips back, it's going back into field. Yep.
So you're applying just like one burst of the B1 electromagnetic field, or is it oscillating?
It really depends on the experiment. There are hundreds of different NMR experiments. Right now I'm just explaining the overall concept of, in all NMR experiments, you have a larger magnet and then another electromagnetic field that hits your nuclei off axis to some degree. Yeah. What this graph is called that you get out from an NMR experiment is called a free induction decay. A free induction decay is often referred to as an FID, and it looks like gibberish to pretty much everybody that looks at it. It just looks like a wave that's slowly relaxing. However, what we can do is Fourier transform this into useful data, and that's what we're going to look at primarily when we look at NMR spectra, is not the free induction decay, but rather the Fourier transform data that's the result of, or that results from the free induction decay. All right, so now the fun part. We get to get away from the abstract physics. First thing we've got to do is determine the number of signals that might result from a compound. And the reason behind this is that nuclei in the same chemical environment share the same resonant frequency. So let's take a look at what I mean by this. Let's imagine I've got dichloromethane. Dichloromethane has 2 protons on it, right? We have to ask ourselves whether or not these protons are in the same chemical environment or different chemical environments. What do you guys think?
Can you ask that question again?
So if we're looking at this proton in red and this proton in green, are they in the same chemical environment? Meaning, if you're looking around as the red proton, do you see the same exact environment as the green proton if it were looking around? Ah, it's a little bit tricky, right? If you guys actually broke out your modeling kit, right, you'd remember that this is tetrahedral. So the red hydrogen, when it looks down, it sees a carbon, and then it's got 2 chlorines and a hydrogen below it. The green one, if it looks down, there's a carbon, 2 chlorines, and a hydrogen below it, right? So it really comes back to this Vesper theory that these atoms are actually in the exact same chemical environment, so we only see one signal on the NMR.
So it doesn't matter which side they see it on, as long as the things are there?
Yeah, exactly. So in this case, orientation doesn't really matter a lot. It's relative positioning, right? So HA and HB are in the same chemical environment.
But if one of them were like for example, bromine, then it would be different.
Yes. Well, are you saying if one of the chlorines was a bromine?
One of the hydrogens.
In that case, you would only have one proton signal, right?
Oh.
Yeah. So in this case, because HA and HB are in the same chemical environment, we only observe one signal, right? Let's look at another example. For this example, I've got a carbon, I've got an oxygen, I've got a carbon. And we've got dimethyl ether. We've got a bunch of hydrogens in here, right? We've got 6 of them. Are they in the same chemical environment or different chemical environments?
Oh, carbons?
No, for the hydrogens, not the carbons. It's a little bit tricky, right? If we think about the hydrogen right here, we could argue and we could say, well, this hydrogen is actually closer to this lone pair than this hydrogen. Am I right there? Ah, the sigma bond can rotate, right? So if we took a snapshot in time, we could say, yeah, definitely, that top hydrogen's in a different chemical environment. However, sigma bonds can rotate really, really quickly. And so this spins like an umbrella, or it spins like a helicopter blade, and therefore you can't really distinguish one proton from the other. So how many protons do you think we might see in our NMR spectrum? So we said that all 3 of these are likely the same because they spin like a blade, a helicopter blade. Are they the same as these guys?
Yes.
Yeah.
Why?
Meso compound.
It's not a meso compound. There are no stereocenters. However, it does have a plane of symmetry, right?
Yeah.
So in this case, because of the symmetry element in this molecule, they're technically in the exact same chemical environment. So if we look at these, we could say that we would only expect one signal because all the protons are in the same chemical environment, meaning we'll only get one signal. What about for our carbons? How many carbon signals do you think we might see with NMR? One? Why is that?
Same reason.
Same reason. With carbon, we've got symmetry and they're in the same chemical environment, therefore we'd only see one carbon signal. Right now you're probably thinking this is pretty boring. Why are you so excited about this? But let's take a look at some different examples, and this is where things get interesting. Nuclei in different chemical environments have different resonant frequencies. So I'll choose everybody's favorite alcohol, ethanol. And we've got these guys sticking up. We've got some other hydrogens over here. Now the question is, how many unique protons are in this molecule?
3.
Okay, let's take a look. If we look at this proton, are there any other protons in the exact same chemical environment? Meaning, are there any other protons that are directly bonded to an oxygen with all the same neighbors and everything? No. So that one's unique. So we'll see a proton corresponding to that red guy. All right, what about this proton over here in blue? Are there any other protons in the exact same chemical environment?
Yes.
Which one? The one pointed back, right? So the one pointed back is still attached to a carbon that's one bond away from a methyl group and an alcohol. So both of those blue protons are in the exact same chemical environment. They're just facing different sides of the molecule, right?
Yep.
And then the last one, are there any other protons that are just like that green one?
The rest of the 2.
Yeah, the remaining 2, because like we said, methyl groups can spin like helicopter blades, and because of that, they average out and they're pretty much in the same chemical environment. So in this case, we would observe 3 different proton signals in NMR. And you may notice with proton, I always indicate it as 1H, meaning it's the isotope of hydrogen with a mass of 1. Why don't I have 2H? Because it's even, right? We can only observe things that have an odd number of protons and neutrons.
Is there a way to understand why that is?
That's getting into kind of complicated physics. We're not going to talk about it much in this course. Yeah, we can talk about it later if you want, though. All right. What about for carbon? How many carbon NMR signals might we see? 2. Right? Because if we look at this, we've got this carbon here and this carbon here. They're in different chemical environments. And we would observe 2 different carbon signals. Do you think we're going to observe carbon-12? No, because it's an even number, right? Do you think we're going to observe carbon-14? No, because again, it's an even number and it's only in part per trillion level. What isotope of carbon do you think we're likely going to observe? 13. So whenever we do carbon NMR, we're always observing carbon-13 isotopes, which are approximately what percentage of all carbons?
1.
About 1%. So carbon NMR is inherently less sensitive because it's only picking up 1% of the carbon samples in solution, right? Proton NMR is great. It takes a matter of seconds to run. You can see very clearly where your peaks are. Carbon NMRs, oftentimes you actually have to run them overnight before you can get a clear signal out because it takes hundreds of scans before you can get good data.
How do you know the carbon is certain?
Because NMR can only see odd number of protons and neutrons. That gets into complicated physics. Yeah. Does that make sense? What's?
Does it work for like oxygen too, or?
Yeah, so oxygen-16 you can't see. However, with exotic isotopes of oxygen, you can. It's not very common, though. Same with nitrogen. The most common NMR that you use in organic chemistry is proton and carbon NMR, far and away, because most of the compounds we look at have a relatively high abundance of carbon-13 in them. Granted, it's only 1%, and there's plenty of proton. Oxygen, the other isotopes, are just not nearly abundant enough to be seen. All right, so now I've got a challenge problem. I want you guys to help me determine how many proton signals and how many carbon signals are in paraxylene. So I'll give you guys a minute to work on this, and then we'll try to predict what the NMR maybe looks like. Just for fun, I'm going to draw in all the hydrogens. That's how I have fun. On the weekend, I go home, unwind, and draw myself some hydrogens. The life of a chemistry teacher. So we've got a bunch of hydrogens on here. Yep.
So with the benzene ring, because it's all like partial positive in their resonance, is there only going to be like one hydrogen for each of those, or like for the four?
Yeah, you only have 4 hydrogens coming off of the benzene ring, and you're correct. Those double bonds will actually delocalize throughout the ring, so you can't really think of them as static alkene bonds, right? They're more like bonds and a half all the way through the ring. So if we want, we can even draw it as a hybrid form, like that, just so we're not confused, and we could say those are delocalized. All right, so let's go through these. Are there any other protons like this blue proton?
Yes.
Which one?
The 4 on the ring.
The 4 on the ring. All right, so this one, if you think about it, you're correct. That's on the same side of the ring. It's adjacent to a methyl group. It's next to another hydrogen coming off of a ring. And it's the same as this one, right? Yep. So if we look at all of these, there's actually 2 planes of symmetry in this molecule. There's one going smack down the center, and there's one going horizontally, right? So because of that, all 4 protons coming off of the ring are equivalent.
So we would take resonance into consideration.
Yeah, in this case, they're not going to be different because of double bond location, because the double bonds are completely delocalized around the ring. All right, what about these protons?
Yes.
Are they similar? We know that all 3 of these methyl group ones are similar. And they're identical to the ones on the top, right? Because of that horizontal plane of symmetry. So if we look at this, we could say, all right, there will be 2 sets, or 2 different 1H signals. All right, how many carbon NMR signals will we have? 3. So if we look at this, we would have this green one, right? And it's the same as this one down here. And then we'd have this blue one right here. That's the same as this one. And then we would have this red one. That's the same as all of these, right? Because of all the symmetry elements in there. So we could say that we have 3 different carbon-13 signals. All right, so before we head out really quick, let's just take a quick look at what the spectrum might look like. The scale that we use in NMR is typically in ppm, which is parts per million. Less commonly, you'll see it in hertz, and even less commonly, you'll see it in tau. But most of the time, when you look at NMR, the spectrum's in ppm. The scale goes typically from about 15 to 0 for proton NMR. And in this case, we can break it up. We should expect 2 signals. So if we look at this compound via NMR, we might actually predict a signal that's like right around here, and we might observe another one that's maybe down here. So what we're going to do tomorrow when we come in is learn how to predict where on the scale signals will show up. And then we'll also learn how to interpret what those signals mean and how they can give you some clues as to the connectivity of the overall molecule. All right, I'll see you guys in lab. I know some of you had questions about lab. You don't have to prepare your lab notebook. It's just going to be an in-class activity.